Alright. Particles having a size of 0.1 millimeter, sphericity of 0.86, and a density of 1,200 kilogram per cubic meter are to be fluidized using air at 25 degrees Celsius and 202.65 kilopascal absolute pressure. The void fraction at minimum fluidizing conditions is 0.43. The bed diameter 0.60 meters, and the bed contains 350 kilograms of solids. What you're asked to solve for are the following. Calculate the minimum height of the fluidized bed. Calculate the pressure drop at minimum fluidizing conditions. Calculate the minimum velocity for fluidization. And using 4 times of the minimum velocity, estimate the porosity of the bed. So let's go to the given. Basically, what you're given are the density, 0.1 millimeters, the diameter, 0.1 millimeters. Density is 1,200 kilograms per cubic meter. The sphericity is 0.86. The porosity is given, or the voidage is given at 0.43. And then the diameter of the bed is given to be 0.6 meters. And then the properties of air at 25 degrees Celsius is given. So the absolute pressure was already provided to us, 202.65 kilopascal. The density is 2.372 kilograms per cubic meter. And lastly, the viscosity, 1.845 times 10 to the negative 5 Pascal second. So what are we asked to solve for? You are required to solve for the bed height. Sometimes you can see in some books H, sometimes it's L length. You're asked to solve for the minimum fluidizing pressure drop, and then fluidizing velocity, and the void fraction when V is equal to 4.0 times the VOM. So in here, basically what you have is, is the diameter. It's given to be 0.6 meters. And then what else is given? The others are already given. Here, you would want to solve for the V, right? So let's try solving. So in order to solve for the first ones, the LM or HM, we can use this given relationship, this given formula. And isn't it that, as I mentioned earlier, for pure solid, if it was to be assumed to be pure solid, what happens is E1 for pure solid would be equal to 0, right? So we would want to solve for LM. The thing is, we don't know what L1 is. We're not given any L. So what we can do is, we know that volume of the solid is equal to mass of the solid over the density of the solid. And you were given the mass of the solid. It is given to be 350 kilograms. And then this is given to be 1,200 kilograms per cubic meter. Therefore, this is 0.2917 cubic meters, the volume of the solids. V is area times length, right? So we can say length 1. So we know that V is given to be 0.2917, and then the area is pi over 4, and then that's 0.6 meters squared, L1. So you can solve for your L1, which is 1.0317 meters. So now we can use the given in here. So L1, 1.0317 all over LM is 1 minus EM. What's EM? Because at the fluidization, it would be 0.43. But for our approximation, L1, E1 would be 0 at L1. So it's this one. Therefore, LM is simply 1.0317 over 1 minus 0.43. What is LM? LM is 1.81 meters. So that's the answer for letter A. For letter B, what's being asked? The pressure drop at minimum fluidizing conditions. So the pressure drop, I already wrote here the formula for pressure drop. Delta P, I can just multiply the LM to the other side. We were able to solve LM earlier, 1.81. So let's just note here LM from letter A. 1 minus EM, which is 0.43. This is 1,200. What's the density? 2.372. 0.372 times 9.81 over 1. Therefore, your delta P is 12,121 Pascal or 12.12 kilopascal. So that's the pressure drop at minimum fluidizing conditions. So let's go to the third. What's the minimum fluidizing velocity? So in order to solve this one, let's just use this formula. So let's just plug in whatever's given to us. So 150, and then the viscosity is given to be 1.845 times 10 to the negative 5. And then this is what you're solving for. 1 minus E, which is 0.43. So I'll just separate that from the first. The sphericity was 0.86, and then the diameter is 0.1. 0.86 squared, 0.1 times 10 to the negative 3 squared. This is 0.43 cubed plus 1.75 V squared over 0.86 times 0.1 times 10 to the negative 3. That's 1 over 0.43 cubed is equal to 9.81 times 1,200 minus 2.372. All right. So you'd be able to solve for the minimum fluidizing velocity. This one should be 4.375 times 10 to the negative 3 meters per second. You'll notice, guys, that this one is actually a quadratic equation. So what I usually do is I solve for this one, all the constants, the coefficients, and then this one I solve for all the coefficients and then input them as quadratic equation in the equation solver, because sometimes there may be calculators that can't do solving for this one. Next is you're asked to solve for the porosity or the voidage when the velocity given is 4 times the minimum fluidizing velocity. So if it's 4 times the minimum fluidizing velocity, your VO is 4 times the VOM. What is that? 4.375 times 10 to the negative 3. 4 times 4.375 times 10 to the negative 3. This gives us 0.0175 meters per second. So this is what we plug in here, because now, because the fluidizing velocity, if it's minimum at this minimum fluidizing velocity, that would have been the porosity in between the particles. But what happens is that because you increased the velocity to a much higher velocity, 4 times the minimum, if the velocity is increased, will the porosity be bigger or be smaller? Okay, so let's plug in 150 times 1.845, 10 to the negative 5, And then now its VOM is 0.0175, 1 minus E over E cubed. This one at the bottom does not change, 0.86 squared, 0.1 times 10 to the negative 3 squared, and then plus 1.75, 0.0175 squared times density. I forgot to write the density. 2.372 all over 0.86. And then this is 0.1 times 10 to the negative 3. 1 over E cubed is equal to 9.8 times 1200.372. So in here, what I usually do is I solve for this and this to be the coefficient. And then the E cube, I move the E cube to the other side and then use equation solver. So you'd be able to solve for E is equal to 0.60498, or basically 0.605. So again, because of the increased velocity, what happens is that the voidage increased. Imagine it started from 0.43 for minimum fluidization, and then it became 0.605.